Very pleased to hand over to our next speaker to introduce Professor Cristina Lazzeroni from the University of Birmingham.
Thank you and good afternoon. And so I will talk about, I will touch a few things that I've already mentioned today, possibly from a bit of a different angle. And specifically, I will try to argue on my side the sort of a role of importance of broken symmetries. And so today we talk about quite a lot of symmetries, and we have already touched on the idea of broken symmetries. But somehow, I came to this conference with a clear preconception of mine that symmetries are fundamental for the understanding of how things work, at least my understanding. But I also would like to argue today that broken symmetry are perhaps at the same level of importance, if not more, again, to understand really how things work around us. And to do so, I will just put towards you some examples from my own field of research, which is particle physics. So first of all, let me go back to something that is already mentioned to some of the speakers, and that's undoubtedly you know from a long time, probably, which is what are the elementary particles. So Temis was touching on this earlier on. And so we know that we have 6 quarks and 6 leptons and 4 force carriers, and that is what we call the standard model of particle physics. And despite having so very little ingredients to be a comprehensive model that describes basically very successfully and entirely the world of particle physics, there is also some oddities, and in a sense, it doesn't look particularly well structured if you look at it like this. Somehow, you see the mass of the particle, which is sort of represented here for these blobs, don't have any particular very evident structure. Besides, one may wonder why you got leptons and quarks, and why, in general, these things have some degrees of, a big picture around it. And so the first thing I want to mention is that, so in fact, symmetries, I would say that the first important symmetry is already there under your eyes when I show what I call the particle zoo. And we go back to the idea of permutation symmetry, that is basically the first non-space-time symmetry was introduced by Heisenberg in 1926 in relation to the fact that you can swap basically 2 identical electrons in an atomic system, so they are indistinguishable. And so that is, in fact, basically at the core of what we call the Bose-Einstein and Fermi-Dirac quantum statistics. And so that gives the behavior of an ensemble of indistinguishable particles that are either bosons or fermions, and they're basically distinguishable because there are 2 different possible ways with which they can aggregate or not. So bosons will aggregate and can occupy a single quantum state, where fermions, where these Fermi-Dirac statistics, they do not. And so, in fact, what is then become clear is this is related to what we call particle spin. So in a quantum mechanical system like elementary particle, they have an intrinsic angular momentum that basically you can imagine a figure in your mind that they sort of spin, and they have an angular momentum that is not the same as the orbital angular momentum. That was introduced by Pauli in 1924 as a new degree of freedom. And again, in 1927, Pauli formulated the theory of spin. And in 28, Dirac described that the electron as a relativistic fermionic system. And indeed, in 1940, finally, we proved that the spin statistic theory that fermions have half integer spin and bosons have integer spin. And so if you have this in the back of your mind, then suddenly the particle zoo that I showed one slide before has a different meaning altogether. Because you know that ordinary matter, one that you find, for example, in atoms, those are all made of fermions. So your neutrons, protons, electrons, and so on are fermions, and then they held together by something that are bosons that represent the forces of the Standard Model. And so, for example, the gluons, the photons, and the weak interaction carriers, the Z and the W, are all bosons. And so, in fact, there is this sort of, in a sense, dual world of the particle physics between fermions and bosons, and this is something that I will come back towards the end of my talk. Now, let's move to some of the symmetry that are explicitly broken. So the first that we already mentioned today is parity, and indeed, mathematically, is a reflection through the coordinates, the origin of the coordinate system. As Temis already mentioned, this is not the usual image in a mirror, although if you, for example, Google the internet, you always find these kind of pictures here. But then we are not quite surprised by the idea of parity, and this is because of, I think, quite an important point, that we are used to parity. We are used to see ourselves nowadays probably in a mirror, maybe not so, centuries ago, but still the fact is at the fundamental level that at the fundamental level of the human scale, so for example, the electromagnetic force, the atomic reality that we are around us, that respect parity. So that there is a parity conservation. So we are used to the idea of parity. And in fact, the parity was rediscovered in the quantum context in 1927 by Wigner, who interpreted spectroscopic result as permutation, rotation, and reflection. But it remains the fact that fundamental laws, for example, of gravity, electromagnetism, and the strong interaction are invariant under parity. So somehow we are used to this. And Temis already thought you can think about a clock and a conservation of parity in a clock, and you can have parity violation. But in fact, in 1956, Lee and Young pointed out that the famous beta decays were not being tested for parity violation. And so shortly after, an experiment was performed by Madame Fu, where showed that indeed parity is violated in these beta decays of a polarized cobalt-60 nuclei. And in particular, what does it mean? It basically, in a beta decay, you'll have electrons emitted, and if you put the whole thing in a magnetic field, it basically shows that the electrons are emitted preferentially in the direction opposite to the applied field. So essentially, whatever you look at this experiment, it means that one experimental outcome is more probable than another. So there is a violation of what you would call this complete parity inversion. And because if parity was conserved, you would expect equal rate of producing the electron in the direction opposite all along the nuclear spin. And this is not true. Now, we know that ultimately is due to the charge with current acting at the elementary level of the particle of the beta decays. But fundamentally, that means that it's 100% violation of parity symmetry. So really, the weak interaction distinguish completely 100% one direction with respect to the other. Okay, so that, as we touched already this morning, has to do for us to the problem of chirality. So your right hand is the same or not of your left hand. This is a huge debate and problem because, as was mentioned this morning earlier on, as mentioned by Kant, for example, so your hands, in a word, if you were to produce a word with just your right hand or just your left hand, the two words would be identical. But then, okay, so already the fact that the world may not be so identical, but in fact chiral, is per se quite a huge concept. But in fact, we now come to the charge conjugation. And the charge conjugation replaces particles with antiparticles. And then this charge conjugation arises because, in fact, for a given particle and its antiparticle, generally what you do to go from one to the other is just swap the electric charge. Okay, so, and in fact, as Themis mentioned earlier, a lot of experiment came after the famous experiment of Madame Wu, and it showed that, yes, also charge conjugation is maximally violated. And so one comes to think, okay, fine, so parity is maximally violated, charge conjugation also, but if you put the two together, you get CP. And so as long as you've got the CP operation is a good symmetry, then you still retain the possibility, the absolute distinction between left-handed and right-handed coordinate can be avoided, okay? But now let's go back and look a bit closer at what happens with antimatter. And so, and again, maybe here we touch a little bit on what comes first in a discovery. Theory over experiments, and the history has told us that it can be both in various order. But again, so the history of antimatter starts in Cambridge in 1928, when Dirac predicted the existence of a positron. And as Themis would tell you this morning, because of CPT, matter and antimatter are supposed to have the same mass. But in putting together quantum mechanics and special relativity in what is called the Dirac equation, you predict the existence of antimatter. And that was a prediction. But then, in 1933, in a picture like this, in a bubble chamber, we indeed found antimatter. So then antimatter is real, it exists, you can see it, you can measure it. So every fundamental matter particles, by the way, has its antimatter. And it's all very simple, right? As for virtue of the CPT theorem, they have opposite charge, same mass, same lifetime. But are they really so symmetric? That is the basic question. So in fact, we know, and we can prove, we can see, that if a particle and an antiparticle, each of mass m, collide, they annihilate. So they just form energy in the form of radiation, right? With the famous Einstein equation, E equal to mc squared. Okay, the opposite is also true. This is what we do. I'm an experimental particle physicist, so colliders is what they do. Every day you take energy and you produce particles and so on. Okay, so, but what I can tell you is that one always creates matter and antimatter in equal amount. So far, every experiment has created an equal amount of matter and antimatter are always produced, right? And that is, for example, a picture from the LEP collider at CERN. And you see that, you know that there's matter and antimatter because they're exactly back to back. So they balance each other perfectly. And so you know that, you know for sure, you can measure that every time you produce an electron, there is a positron. So far, so good. So by extrapolation, like humans try to do sometimes, that we say there is no real reason to say that anything different than that has ever happened. And therefore, we could conclude maybe that this is what happens in general. The matter and antimatter are always produced in equal amount. But the fact is that if we look around us, the universe is made of matter. There is no question about it again. By observations, you can see there is virtually no antimatter whatsoever in the universe. So clearly, the antimatter world is simply not there, right? Not that we can see, at least. So something has happened. And this something is the CP violation that Themis mentioned before, and I want to come back a little bit more in detail about it. So immediately after the Big Bang, matter and antimatter were not exactly equal. And please note the presence of this one on the matter side that is not there on the antimatter side. And then at this point, the great annihilation begins. And at the end of it, the symmetry is broken. And that one there, because of the virtue of antimatter, that one there is the whole universe. So in a sense, well, if that wasn't there, we will not be here discussing this conference. So essentially, this is really the CP violation has a huge impact on what happens. And if we look at what happens in the timeline of the universe was equal to start with. Then CP violation makes a slightly difference between matter and antimatter. Then the great annihilation happens, and then that's it. The universe contains only matter. So what is really CP violation? And sometimes I use this optical analogy to say that this is a very clever picture from Herschel, clearly not mine. But so this picture with horses is basically a representation of CP conservation. So for parity, you will indulge with me in taking as a mirror. So you just take the mirror image and see charge conjugation, you swap black and white. And you do a similar action with the ducks below. And then while the first image with the horses is identical to the last, so CP is conserved, the images with the ducks are not, because Herschel images are really very clever. And he managed to incorporate CP violation in it. And so the tail of the duck is in different directions, as you can see. And so now so this is great in principle, but as an experimentalist, I want to measure it. And so to measure it, we need to go back to basics. And so we look at particles called hadrons that are made up by quarks. And so there are two kinds that we know of. Well, nowadays we know more kinds, but fundamentally we can talk about baryons, was 3 quarks, or mesons, quark and anti-quark. And why I am talking about quarks? Because so far the only source of CP violation is in the quark sector. We haven't yet seen anything like this in leptons. And so historically, CP violation has been observed, first of all, in the system of the neutral kaons. And so kaons are particles containing the strange quark. So why the quark was called strange? Well, because these particles were discovered firstly in cosmic rays. And they're called strange because they were produced very rapidly, because they are produced by strong interactions, so very, very rapidly. But they actually decay. They take a very long time, relatively speaking, to decay, because they decay by weak interaction. And this bizarre behavior that they're very quick to be produced but very long to decay gained them the name of strange. Now, depending what type of quark is in there, either S or S bar, so strange or anti-strange, we call them K0 and K0 bar. Okay? But in fact, it happens that they undergo a quantum mechanics system, phenomena called mixture. So what they do, you start with one, but they can actually transform at any time in the other and vice versa. It's called a quantum mechanical mixture of K0, K0 bar. But then again, the Kaons system is more complex than this, in fact, and the particle that you observe decaying are in fact not the K0 bar, but other objects that we call K short and K long. Why we call it K short and K long? Well, they are a mixture of K0 and K0 bar, but they have a very, very different lifetime, right? So one is of the order of 10 to the minus 10 seconds, the other 10 to the minus 8 seconds. So there is a clear difference. Now, at that time, when this particle were discovered and studied, Gell-Mann specifically and other colleagues realized that the fact that this particle contains S and S bar means that they interact differently with matter. They have different probability of interacting with matter. You also realize, therefore, that if you start with a beam of mixture, that any Kaons you like, because you can distinguish between K short and K long, so one has very different lifetime. If you leave them long enough, the K short will be gone, and you only remains with the K long. Okay? But then, if you pass this beam again through matter, because the K long has the K0 and the K0 bar, so he has both S and S bar, you will have the process called regeneration. So the two bits of it, the K0 and the K0 bar, will interact differently with matter. And so, interestingly, at the end of your experiment, you'll find again some of these guys of the K short, because they regenerate through matter. So this is what people knew pretty much at this time, or at least they thought they knew. Okay, so then we come to this discovery that shocked the world, as Themis put it, by Fitch, Cronin, and Turley in 1964. And first of all, let me say that this is were three people with very, very different background. So Fitch and Cronin were basically detector experts, especially Cronin. So he had a brilliant kit, a splendid particle detector, all new, that could be useful to this measurement. And what they wanted to study, right, they didn't at all wanted to discover the CP violation. Nobody had any idea about it. What they wanted to study was the process of regeneration, the one that I just described, okay? And so, right, so they set this experiment. The experiment was approved with pretty much 1 page or so proposal, which is shocking for many of us. And nowadays we write 150 pages to make a new experiment, at least, and was approved for 200 hours of data taking. And in fact, they only spent a few, very limited amount of hours to look for something else that was a secondary aim of their experiment, only if they had time, which is if we assume CP invariant, then the K long, right, the one that lives longer, is forbidden to decay to 2 pi m. And this is also why it has such a long lifetime, people thought. Right, while the K short decays very rapidly into 2 pi. So this guy sets the experiment, and after a certain length, all the K shorts are gone, and you remain with the K long. And then, surprise, surprise, they measure 45 2 pi events. And there is no question that this is an observation of something that it was never going to be foreseen. Okay, so it's a clear statistical evidence that the K long decays into 2 pi m's. Right. So that was indeed a big discovery that nobody thought was going to happen. In fact, as I said, they were completely looking for something else. So then, this is what's called the CP violation in the mixing, because it's all related, at least conceptually, to the mix of K0 and K0 bar. And so you wonder if that was the end of the story of CP violation. Well, no, it's not. And in fact, for years, there was the debate if there is also CP violation directly in the decay of the kaon. And the answer is yes. And it was measured by the NA48 experiment at CERN and also the KTEV experiment in the US. And so, no, the CP violation is extremely varied and quite complex. So the original CP violation parameterized by something that's not very originally probably in physics called epsilon. It's of the order of 10 to the minus 3. Direct CP violation is of the order of 10 to the minus 6. And here we have still a big problem, because the amount of CP violation does not explain the imbalance of the universe by any stretch of imagination. So the problem is still open. Nonetheless, from the conceptual point of view, CP violation, the discovery of CP violation leads to the conclusion that the microscopic world distinguished between right-handed and left-handed coordinates. Okay? So that is something that cannot be recovered at this point. But on the other hand, I would argue that it's thanks to CP violation in many ways that we are here discussing about it. Now, another broken symmetry that has a huge impact on our existence, I would claim, is something that is called spontaneous symmetry breaking. And let me go there for the remainder of my talk just quickly. So first of all, let's go back to the so-called Buridan-Axe paradox. So you take a donkey and it's placed in a perfectly symmetric position between two equivalent bundles of hay. And the donkey has no reason to choose between one or another. And so not being able to choose, remains in the middle and dies of starvation. So I expect you to say, okay, really? Well, the point being that, in fact, we know that any sensible donkey will eat both, right? But the problem is that the story here implies that the two situations, the left and right situation, are completely equivalent, okay? So that's why the donkey is not able to decide. Right. And so, as Pierre Curie put in 1894, asymmetry is what creates a phenomenon. So, for some whatever reason, a real donkey will think that the left A is better than the right A and eat that one first and then the other. So, the problem will not be there. But so, what has this to do with our symmetries? Well, okay, so far, we talk about of P and C, which CP, which is an explicitly symmetry breaking. So you put the symmetry breaking terms by hand on the basis of your results, right? But you can also do, and there are other ways to introduce this explicitly symmetry breaking. But you can also have spontaneous symmetry breaking, okay? When a symmetry have solution of your equation that do not respect the general symmetry. So for example, if we take a linear vertical stick and you apply a force top and bottom to it, at a certain point it will buckle. Right, and so the linear vertical stick has a rotation symmetry, but clearly when it buckles, you break the symmetry and it goes in a state that is not symmetrical. However, you can move to any other equivalent states by rotation. But the lowest energy in which it collapses, because it buckles, is not itself symmetric by rotation. Okay, so that is spontaneous symmetry breaking idea, and this has a lot to do in quantum field theory with the Higgs field. And so the Higgs field is a quantum field that basically then the Higgs boson is the carrier of the field, and that it has to do with basically in quantum mechanics, the ground state of the buckle becomes the vacuum quantum states. And the point here is that you may have symmetries in nature that you do not realize simply because you live in a world in where your ground state or vacuum quantum states do not satisfy those symmetries, okay? But the fact that the symmetry is spontaneously broken doesn't mean that it doesn't exist as a symmetry. Okay, so then this has to do also with the Higgs potential that is famously thought about like a Mexican hat. Potential, where if you think you have a ball at the top and you let it go, at any moment it can go in any direction of the Mexican hat, but it will decide by itself to go in one particular position. And so when it falls, a particular direction is chosen and the symmetry is broken. Okay? That in a very complicated way that I will leave to the theory people in this room is related to give particle masses. Right? And so the Higgs mass mechanism is basically what gives particle the mass. And essentially, the mass is a measure of the interaction of the particle with the Higgs field that permeates the space. But what I would like to argue here is that if you think for a moment of the stability of the atom, right? And we, if you remind ourselves of the Bohr radius of the atom, if you put the mass of the electron to 0, there is no stability in the atom. The atom is not stable. So without the Higgs boson, this is the best example that I could find of broken symmetry that actually, for the Higgs boson itself, that gives structure to the universe. And so once more, without the Higgs boson, we would not have structure. So the Higgs boson, or something comparable to the Higgs boson, well, consistent with the Higgs boson, has been discovered in 2012 at the Large Hadron Collider, and with a mass measured of the order of 125 GeV. And so far, in fact, this particle is consistent with the Higgs boson prediction of the Standard Model. We haven't found, sadly, nothing that tells us yet otherwise. But so now for the last maybe 1 minute of my talk, well, the mass of the Higgs is 125. And in fact, this is a bit of a problem again. why the Higgs boson should be so light. Because in fact, clearly it interacts with particles to give them mass, and in fact, then it would be itself really very heavy. But in fact, it's not, it's just 125 GeV. So the idea that has been around for quite a time is that you have another symmetry, right, that relates boson with fermions and fermions with boson, and it's called supersymmetry. And so with additional particles would cancel the contribution to the Higgs mass and stabilize the Higgs mass to the value that it should be. Again, this is basically, it's like a hidden world of supersymmetric particles that are counterpart of what we know. So for every quarks, there is, for every leptons, there is a boson, and vice versa. For every boson, there is a corresponding lepton. In fact, it's lepton because it's supersymmetric. So again, we go back to what we said at the beginning of the talk, that the particle world as leptons and quarks. Well, okay, in fact, supersymmetry links the two. There are two different classes of fermions and bosons that are heavier of the counterpart. And because they're heavy and they need mass, otherwise we would have seen it in a long time, again, supersymmetry needs to be broken. Now, the supersymmetry is not yet observed, and by the way, now there are other models of new particles that we are trying to find and investigate. And so that's the end of my talk, and at least with two examples of things that we have measured, so we know that they exist, I'd like to claim that broken symmetry are indeed extremely essential for the existence of our world. Thank you.
Right, we have some time now for questions. And who's going to kick us off? We'll start over there.
Can I just clarify one of the threads of the argument?
Yeah.
We want to explain the asymmetry between matter and antimatter in order to explain our existence, essentially. You say that that requires CP violation. You then present us with evidence that CP symmetry is violated.
Yeah.
But you then say that that's not enough.
Yes.
So why isn't it enough, and what more do you need?
Yes, so thank you very much. That is a Nobel Prize question. So I don't have an answer to that. I do know that clearly there is a difference between matter and antimatter, and so you can make legitimately model and then you measure this difference. The point is that to look at the asymmetry that there is in the universe, the amount of CP that we measure is far too short. But I was saying that we haven't yet seen it in the lepton sector. And so we got experiments out there trying to find, for example, CP violation in the lepton sector. So that it will be something if we find it. But I cannot preempt the result of the experiment, which we'll have to say what they find. If it's not in a lepton sector, then we will have to look a bit more, imaginative way. But yeah, the lepton sector is a possibility. We shall see, not in a long time, I would say.
Another question over there, just behind you.
Would you say that parity violation is an indication that those symmetries aren't there, or we are in a vacuum where it's spontaneously broken? So
for parity violation, there is certain things in physics conserve parity. So parity symmetry is still perfectly fine, for example, for electromagnetic interaction. That's not a problem. But the weak interaction violate it maximally. So, when you ask about symmetry, I think one has to think about symmetry for what. So for the electromagnetic interaction, certainly there is no problem that we can see, at least, and good limits as well. But for weak interactions, which, for example, it's the beta decays and so on, this is maximally violated. So in general, I cannot say that parity is a universal symmetry everywhere. I can say where is conserved and where is violated.
But is it spontaneously broken, or
No. The parity is explicitly broken. The other spontaneously broken is the Higgs boson style.
There's a question just behind you on your left.
As it's a conference about history, I was interested in the mass of the positron. I mean, the way that we present Dirac's equation and the positron comes out today, it seems almost self-evident that the positron's mass is the same as that of the electron. And yet, as I understood it, Dirac, for some period, considered the proton was what he was talking about, which clearly does not have the same mass. Now,
Yeah.
Is that actually folklore, or was it just the discovery of the positron empirically that pointed people towards it having the same mass, or what? Where exactly, at which point did the symmetry come in?
So I would leave that to the historian of physics, actually. I only have one comment that indeed, I think in the history of physics has many of these examples that particles are first thought about there's something else and then you name it. So, for example, the pion is another one that people thought maybe it was something else, the Kaons also. So, to my students, a week ago, I was saying, at some point, people was looking at the tritium going to helium and the decay of that, the beta decay of that, and the scientists at that time were pretty much on the point of throwing away the conservation of energy and momentum, which would be completely crazy, right? And then we discovered the neutrino. So yes, I would say, it's true. I think I put it a bit too easy, but indeed, the route to one understand it goes not necessarily in a linear way, but yes, I think I will leave.
Do you want to come in on that?
Yeah.
Yeah? Can we get a microphone down there?
Yes, thank you very much for this talk. I want to underline the connection of your message to symmetries again, because you underline the importance of spontaneous symmetry breaking. And insofar, the evolution, the cosmic evolution, can be understood as spontaneous symmetry breaking, and that means as a decay of symmetries. In connection with the gauge symmetries, we can characterize each of the fundamental forces by gauge symmetries. And that means by groups like SU2, SU3, yes, and so on and so on. And so most of this kind of bifurcation in these groups is confirmed by experiments in high-energy physics. But of course, the last idea, namely the unification of all these partial symmetries and groups in something like a unified group, what about that? Is it a kind of supersymmetry? What is your idea concerning this kind of unification of all these symmetries?
Well, I'm not a theoretician, I'm a simple experimentalist. But, so yeah, it's true that one effect of supersymmetry, if exists, is that it would lead to the grand unification. So to the fact that, as you say, the point is different scales with different energy scales which you measure or you see things happening. And at the moment, we are looking at the energy scale that we can see. But if supersymmetry indeed exists, it can lead to the unification of all the forces at a certain mass scales. But the point is, I don't know, because we haven't seen supersymmetry. And to go back to a question I think there was this morning, have we disproved supersymmetry? Okay, my very humble experimentalist point of view is that it's very difficult to disprove it ever. Is simply because you can always think that supersymmetry is realized at an energy scale that is not accessible to the experiment. And it would be very, very hard to disprove this statement, because you can always push your boundary of supersymmetry to an energy scales that is way off what you can ever do. So I don't think you can, but on the other hand, perhaps we should reverse the question and say, okay, so if supersymmetry is not realized at an energy where we can see it, is it really a useful theory? So I think rather than true or false, I would perhaps advocate if this is the theory that we need at our mass scale or not.
Any more questions? There's one down here.
I think it's true that there is no satisfactory theory of how supersymmetry comes to be broken, if it does exist.
Yeah.
Is that correct?
Yes, yes, but yeah. So there's various model of breaking supersymmetry, and yes, there are very plausible models of broken supersymmetry. But the only thing that I can say at the moment is that we have not seen it; has not been seen. So there is good limits of huge representations of supersymmetries in the various particles in which it would manifest itself, but clearly up to a certain energy. Now, I must say, not just the energy, because there are colliders, you can do direct investigation with a collider that has a certain energy, and that would lead to certain limits. But as Themis was saying earlier on this morning, you can do different kind of experiment where implicitly you can push your energy scale investigation higher. And even then, we haven't yet seen supersymmetry. So I'm afraid the question is still out there if it exists or not.
If one had a good theory of the mechanism by which supersymmetry was broken, one might have an idea then as to at which energies one would have to go to see it.
I mean, I must also say that supersymmetry is not just the only theory that would, for example, regularize the Higgs boson, or in fact, many other things. One that has lately, I think, become very popular is leptoquarks. So the existence of, again, something else that would, but you see, both have in common, in a sense, the point that you're trying to link two apparently separate universes, the lepton and the quarks. Either with an explicitly doubling the world, like supersymmetry, or with creating direct links between lepton and quarks. And the jury is out there. I don't know.
Okay. See another question up there, up at the top there.
One of the fundamental symmetries in physics is the isotropy of space. All the fundamental interactions, all of the equations for all of the fundamental interactions in physics fail to pick out a privileged direction in space. And yet when I look at my line of sight and I move my line of sight, I see very different things. So the furniture of the world, as it were, the distribution of matter, is not isotropic. At least locally, it's not isotropic. Now, we don't so much worry about this, maybe because we think it's a kind of spontaneous broken symmetry. Maybe it goes back to the initial conditions of the universe. Why is the asymmetry between matter and antimatter any different?
Well, so I should really leave to this answer to somebody theoretical physicist. But to me, my simple opinion, again, which is okay, it's true. I mean, when I look at the picture of the cosmic microwave background, it's symmetric within some extent, but there is local asymmetries, and it's like your right and left hand, they're not the same, so not necessarily, but I never pretended that the vacuum quantum state or the world I'm in is necessarily entirely symmetric. But I think the CP violation type of thing is a little bit different, because that tells me inequivalently, like Feynman would say, if an anti-alien comes, do I know if he's an alien or an anti-alien? And yes, I do. So in a sense, it gives me an absolute measure. I think this is the difference. But again, I leave to the audience if they have more elaborate answer.
Okay. A question down here and then another one up there. So should we go down here first?
I just had a comment that we know from energy density in the universe, from the microwave background, that the number has to be 10 to the minus 8 times 10 to the minus 9.
Yes.
The comment to that gentleman up there.
Yeah, I agree. Yeah. Yes, the limit on the antimatter, yes? Yeah. Yes, it's very, very little antimatter visible in the universe. With the assumption, going back to what was said to the previous question, that the universe that we see with the cosmic microwave background is obviously a part of it. But again, our principle, generic principle, that we are not special in any possible way, and the bits that we see shouldn't be special in any possible way, then you make the assumption that this is the same everywhere. Which maybe the people in this room, other people may object, but I think this is what in general is said.
I've got one more question here. I might squeeze in one or two more.
You made the comment in your talk that the mass of the Higgs boson is surprisingly light. Now I'm trying to understand. Presumably the Higgs boson gets its mass from its own field. Isn't that a bit incestuous? And
yeah, so that is one thing we haven't yet measured. The self-coupling of the Higgs, well, at least yeah. So we measured the coupling of the Higgs boson with all the other particles pretty much, but the Higgs self-coupling is something that we still need to look at. But yeah, so, okay, again, maybe the expert particle theorist here should answer rather than me. But yeah, no, you're right. Nonetheless, because he interacts with everything, including itself, you would expect a higher mass in this sense, while it's only 123 GeV, and the W and the Z boson are order 80, 90, so it's not a big difference, right? So you wonder why that is. So it's not, yes, but it's not much more massive than, for example, the Z or the W. So that's the basic point.
Just wondered if there's analogy with charge in the electromagnetic field. Does anyone say that the charge is wrong from theory?
Not that I know of, but the other point is that so the Higgs boson might not be unique. Maybe the spontaneously symmetry breaking is more complex than we can at the moment see. There is no, at the moment, we just don't know, I would say, if there is only one Higgs boson or more than one. You may even have a Higgs doublet, it's its own counterpart with another Higgs particle. So I think the Higgs sector is really in its infancy, and we need to explore it, experimentally at least. There is no question, it's just, yeah, it's... discoveries takes many years, and so.
I think we can just squeeze in one more if you're still okay. Yeah, we've got another question up there. Another one there? Okay, maybe one more.
I was just going to make a comment with regards to the question about whether matter-antimatter itself could be an example of spontaneous symmetry breaking. And I think the answer is yes, it could.
It could.
Just to go back a second, it seems we're now talking about astronomy, that the simplest example, I think, for the general public of hidden symmetry is the fact that Newton's law of gravity is three-dimensional. It doesn't care about direction, and yet there's a hell of a lot of spiral galaxies out there. On a case-by-case basis, you're seeing the symmetry being broken. If you plotted the orientations of all the spiral galaxies, presumably they fill the whole of 3 dimensions. It's a question of stability. Nature cares more about stability than about symmetry. Now, with regards to the universe as a whole, I think it's quite possible. Were it not for the empirical fact that we do not see any evidence for annihilation of antimatter clumps out there, I think it could be.
Yeah, it could be. I agree. It could be in principle. It's just it's not in the portion of the universe that we see. whether we want this to make it as a general rule, that since we are not anything special, then by extrapolation it shouldn't be anywhere, but otherwise, yes, it could be.
We have to be on one side of that dip rather than the other.
Yeah, yeah, it could be.
I see one more person wanted to get a question, so let's try and get a final one along that.
Very quick one, still with matter and antimatter. So you mentioned a few minutes ago you don't want to meet an alien, say, to shake hands. Is that true, presumably? You don't want to shake hands with an with an antimatter alien.
Yeah, with an alien, yes.
But if you do come across, if you did happen to come across, say, in outer space with an alien, what question would you ask the alien to determine whether you want to shake hands or not?
Yeah, so it would be admittedly a very weird question, but I would ask the alien if he could please measure the semi-leptonic decays of a kaon, because then that would give me undoubtedly the answer if it's an anti-alien or an alien, and then I will ask him if the particle, the lepton that comes out, is the same that is in his atoms or not. So, but that has, it's a very weird question indeed, and also has the assumption that in the anti-alien universe still has kaon experiments and atoms. So there is some flaws in my questions, I admit.
Right, well, let's thank the speaker. Thank you very much, Cristina.